All right. So that was hydrogen. You see, how many colors did you see? How many lines?
Three.
Some of you 3?
Yes, 3.
Some of you 2, some of you 3. Okay, next I'm going to switch to helium. So that was hydrogen.
Helium or neon?
Is this neon or it got a lot. That's something it's got.
What did you say? You see it's neon? Oh, you're right. Good job. This one is neon. You cannot see. You can hardly see. You're right. It's neon. This one is neon. Okay, right. Was it right? You saw that one? Okay, now I'm going to switch to helium. So try to memorize everything you see. Next week you turn the light on and then you will start answering those questions. And I will be collecting these sheets at the end of that. So turn off neon. Now helium. It's helium.
Blue right next to it.
They don't look very
Someone needs more time on helium?
Yeah, a little more time.
Okay. So again, so at the center of where you should look for the spectrum, in the horizontal direction, the center is a direct light, and then on both sides,
Oh, yeah, there's.
left side and right side, you have this scattered diffraction spectrum. It should be symmetrical.
Green.
And then I'm going to switch to mercury. So turning off helium, that's mercury. Wow. That one, if I remember, we had a lot of lines, right? No? Oh, okay. It was, yeah, it's kind of faint actually. No, it's neon which had a lot of lines, right?
Yeah. What?
Is that dark enough to count?
I mean,
And then finally the last one is going to be argon. This one is very faint too, I mean, but if you concentrate you can see. I wish we have something to block this with.
If you move it up and down, you can kind of tell where it's at. It's like some type of purple.
I see a purple.
Purple water.
Alright, before I turn the lights on again, you would like to see a specific one again? Specific.
Helium?
The helium, which is the coolest one, right?
Well, is that neon?
Oh, neon, sorry. So you want the helium?
Yeah, helium.
And then just for fun, I'm turning neon again. Which I think is the coolest one. Huh?
Yeah, right.
Or mercury science. Yeah.
Yeah, I'm not going to ask you to count those lines, but there are many of them, right? Or maybe you can make an estimate of how many of them you see.
5,000.
You want neon and argon? Okay, neon and argon. Neon and argon together. That was a request. Also,
Can
be
we
careful
just put
because
them all on?
the lamps are not located at the same location, so the center of the spectrum is not at the same location. Anyway, and then I heard a request for all of them together. Okay, that's all of them together. Is that blowing your eyes? Today we are videotaping. I don't know if there is a way to see that through the video, because we are using those ratings, but I don't think if you use that in front of the video, that will be all right. Just enjoy the last few seconds of it. We're going to talk on the light.
I was wondering that too. I was like, well, I can't see any of the other categories.
Is it too right?
Okay,
It's better like that.
yes.
Okay, so let's start answering those questions. Yes. No. And so one of the questions actually on the sheet is what do you see? Let's look at them. Yeah, so let's look at those. Look at those. Put the grading in front of you. So, what do you see? So that's one of the questions here. Is that different? How different is it? What's the main difference? It's continuous? Continuous spectrum? You see any lines? No lines on this one? So that's maybe what you can explain in the answering the questions. Let's go through the questions. So I'll give you 5 minutes to, well, 3 to 5 minutes to do the next. We just did the first step, the engage with the demo. Now, second step, explore. So you can talk to your neighbors if you want. Again, this is the first time I'm doing this activity, so but, so first question is describe the type of spectra you observe through the diffraction rate. So for one keyword, there will be a keyword here that we are expecting. Can you guess what would be the keyword? Quantify, but even discrete is even a better word. And it will not be quantified, it will be quantized. Oh, sorry, I didn't do that. Anyone needs that sheet? Maybe you can still see the spectra. You want me to go to a specific Second question. How many spectral lines did you observe for hydrogen and what are the colors? If you want, I can try to go back to hydrogen and maybe you can see even with the light line. So this is just hydrogen. So how many lines and what are the colors? What colors are those? I wish we could do the activity at the same time, but I have to go back to darkness, and so it's hard to write in the darkness. Let's see, the English is it too dark for you to write down? Is it better to observe something? The next question is, which element has the most spectral lines? Neon? The thing is that some of them, it was very faint, so it was kind of hard to see. Okay. Once you are done with this section, explore, so we can switch to the next section. Section 3, explain. Anyone needs more time on the second one? Okay, let's move on to the third section, explain. So let's try to explain what's going on here. Our first concept is the notion of emission of radiation by atoms. So someone would like to maybe explain what's going on? Michael?
As an electron falls in energy level, it emits a photon with the energy that's lost.
Oh, very good. Next to you, sorry, remember your name?
Seth.
Steph, you want to also add something?
Yeah, I mean, same thing. We're putting energy into the gas, which is what makes it glow, and so the electron jump up and jump
Yeah.
back down. Energy.
So basically, I'm trying to illustrate what you just said. So we have this gas, it's a vapor made of specific atoms, so it could be hydrogen or helium or neutron. And then what's going on with those atoms? So there are electrons in the atoms. You want me to turn off the light here and use the ventilator? Is that too bright? But those electrons, what happens to them in this discharge? They get excited. And then what happens after that?
They move up.
So if we zoom in on the atom, we have the nucleus, and then we are saying that the electrons get excited, so somehow maybe they acquire more energy. And as they acquire more energy, actually, we'll see in a minute how the radius of the orbit is getting bigger in the classical view of it. So it goes from one orbital to another one, bigger one. And then what happens after that? This is the process of excitation. I'm missing the C. Excitation. And then what happens after that?
They go back down
They de-excite. So they lose energy with electrons, so de-excite. De-excitation. And as they de-excite, what will happen? So Michael said that as they de-excite, what will happen? The loss in energy will be transferred into a photon. A photon being emitted, which then relates to the notion of emission of a radiation. So to answer that first question, so this is a process that is allowing those lamps to emit a radiation. So next question. A discrete, or I guess the next notion to explain to a discrete spectrum. What do we mean by a discrete spectrum? How would you represent that? Line. So that's what you saw. So.
Oh, yeah.
Is it an alarm or something? So you saw through the grating a discrete spectrum. How would you represent that physically? Maybe a physical graph. What would you represent on the vertical axis and the horizontal axis? No.
I think intensity would be on the vertical axis.
So intensity of what?
Of the light, and
Of
then
the light.
wavelength as the x-axis.
And it's I, the big I. And then what about the horizontal axis? Lambda, I heard it you say.
Wavelength, yeah.
Yeah, wavelength. The wavelength of the light. Do you think that's what, when you were looking at those wavelengths, that's what you were looking at? Probably, yeah. Because in the diffraction process, that's what it's doing. It's separating the wavelength, the different colors, right? Wavelengths of the light. And so, how would you plot that? Someone would like to come and plot it? Michael? Yeah. Thank you. Very good, very, very good. So can you explain what you did? So it's a bunch of peaks.
Yeah, a bunch of peaks, they're discrete. And I imagined it like a black pipe curve, except these ones aren't being emitted. It's just a discrete wavelength being emitted.
Okay, very good. So you put an envelope, you said you put an envelope on top of it, right? Because not all of those different wavelengths have the same intensity. That's what they said. Right? So you can put that as a dash line together. And then, yes. Yeah, that's how you make a dash line. So, yeah, the notion of discrete spectrum, that is due to what? To the fact that?
It only will emit light at certain wavelengths due to its excitation, de-excitation.
Yes. So specific wavelengths which we could call lambda 1, lambda 2, lambda 3, and so on. Those are, so it's the lines that you see, the spectral lines. Thank you, madam. So here we have the discrete spectrum, because it's not the continuum, has a certain, set of wavelengths. And it's not a continuum like the envelope here is a continuum, but here we are just specific wavelengths. And in between there is no light. And then finally, another notion is the notion of quantization of energy level. While observing a discrete spectrum means is related, how is it related to the notion of quantization of electronic energy levels. So what the connection between this spectrum, which is a spectrum for light, right, for photons, and the notion of quantization for electrons. So the right side is for photons, is what we observe, but then the left side here is about electrons in the atoms. Yes, Brayden?
There are certain allowed energy levels that the electrons can occupy, and if one of the electrons occupying that energy can emit that
That's
wavelength.
right. So, exactly, Brayden. So there will be certain allowed is very important word, energy levels that the electron can occupy here. So meaning here, when we talk about excitation, it can only go to certain orbitals and energy levels. So we have this notion of quantization of energy levels. You can explain that? And so see how we have this analogy with the keyword, the word of this word discrete, which is more like a mathematical word. And which word here? The physical equivalent of discrete. Discrete is a mathematical notion. And here the physical equivalent to it is quantization. Exactly. So whenever you have something discrete going on, it means there's quantization going on physically. And we are going to probably need to introduce then as we describe the quantities, we need to introduce a quantum number, which is going to be an integer, which is going to help us quantize the energy levels of the quantities. And that's what you have here. In the discrete spectrum, you need to introduce a quantum number, an integer, 1, 2, 3, 4. So this integer here, the need of an integer when you have a discrete quantity is going to be transcribed here as a quantum number. That's kind of scary.
It's like it's a presidential national alert.
Oh.
But I'm the only one.
We should all receive that, right? But not only you.
I didn't take out the president, not today.
All right, so then next we can switch to the fourth section, elaborate. So I'll let you answer those questions. I give you a few minutes to answer those. Will any element yield a discrete spectrum? Yeah? Michael?
I would say yes, but I have a question about that too, that some heavier elements, would there be any, like Doppler shifting or line broadening due
Yeah.
to their?
Absolutely. So you might have light water and you might have shifting, absolutely. But if you look very carefully, and when you are looking through the grating, maybe some of those regions they look a bit, fuzzy. But if you look more carefully and with a better resolution apparatus, you will see that they are still discrete. It's just the resolution of the grating and you know, yes. Why heavier elements show more light than lighter elements? Which elements can we compare here in particular? The hydrogen, which is the lightest of all, and then neon was kind of big change between those two. You want to see that one? Can you see like that or can you see? And if I do that right, see the big change? So why? Why then?
There are more electrons in the heavier atoms, so occupying different energies, so there are more.
Yes, and not just that actually, but for hydrogen indeed there is only one electron. While for neon, do you know how many of them there are?
10.
10 of them? Because neon is at the end of the second period, so yes, 10. Yeah, I know, but because of the resolution, and it's also super faint, so the mercury should be heavier. So 10 electrons. So indeed, those, the quantization of the energy levels for neon is going to lead to a more complex set of energy levels than for hydrogen. In a minute, we are going to see how the energy is quantized, and you can represent the energy on the vertical axis, and you will see there will be energy levels like that. So that if you do that for neon, you will end up with more lines, and some of them being split into more than one line. So it would be a more complex set of energy levels. And then in addition, as you say, for them, there are more electrons. But the main reason is initially the set of energy levels themselves. When you solve the system and Schrodinger equation, you will end up with more energy levels. And then indeed, there are more electrons to occupy them. And then so combination. But usually it will be the highest energy, occupied energy levels that will be excited. So it's only one electron at a time anyway, but still because there are more electrons, it's more complicated. Okay, so I'll let you write down the answer for that question. And then what's the next question?
Will a fluorescent or incandescent light lamp produce a discrete spectrum?
Thank you, Kennedy. So you can check that looking at those through the grating. And then what you see, again, we talked about that,
It's not the street.
it's not discrete anymore, right? You don't see lines anymore. Really, it's a continuum. Yes, I don't remember.
Jason,
So Jason.
isn't it still discrete? We just can't distinguish between them?
No, not that one. So you could look more closely with something more resolution. That one is a continuum. Because it's not the same process. It's not a discharge, like the discharge lamp when you excite electrons. It has to do with incandescence and fluorescence. So it's a continuous spectrum in that case.
You can see that the light,
You can see it?
yeah, the fluorescence is discrete,
Oh,
but the incandescents are
yeah.
spectral.
You see some discrete components in them that what you say?
The lines are really, really hard to distinguish.
They overlap, but they're really wide, and there's only four or three.
How to see them? But,
I think the ones over
These
here,
ones.
the ones in the front are not.
oh, because those are not the same. Oh, you look at those, right? Which are not the same. Okay.
Four, right? It's like
But again, it's a combination of various mix of elements, so it's way more complicated than just those lamps. And the process is different as well. Okay, well, I'll let you finish. You have the rest of the hour to finish completing that, and we'll be collecting those.
This is answer to the quiz of the eye.
And then next, I'm going to do the IP now. Quiz. Okay, so here's a quiz question then, kind of summarizing what we have done through this activity. Why do discharge lamps produce discrete spectra? Those are the discharge lamps. Not that, right? Those are not discharge lamps. Those are the discharge lamps. Because they are being excited, we apply voltage into them, and then they have a discharge. Right, me too. Okay, so let's. Anyone needs more time on this one? Or? So we will close the quiz, and it looks like we are missing maybe a couple of you. Okay, I'm going to close it. And let's look at your answers. Okay, we have a majority of you choosing D, and a few of you choosing B. So, okay, so let's go through these different answers. So, because the discharge process is pulsed, so no, usually not, it's static. Here we look at the static process. So it's not that. Because the light is quantized, well, you could say that to some extent, but it's not the origin of it or the cause of it, you know. In the end, we get a discrete spectrum, so showing that the light is quantized, but it's not the reason for it. It's not because you have a diffraction grating, because this is just a tool to look at it. But the correct answer, indeed, most of you found that it's because the energy levels in the atom are quantized. So, good job. And now let's move on to the presentation. So Emma and Ryan, if you want to come. And can I ask you to try to keep your presentation within 10 minutes, you know, maybe between 5 and 10 minutes, so we have time left to discuss the goals tomorrow.
We don't have it on the flashback, so
Okay, so yeah, please come. So while you come and sort things. So just mentioning that this is a phenomenon that is being observed by, you know, scientists in various fields. but one of them is in astronomy, where basically light being emitted by different stars, planets can be analyzed in order to understand what elements are constituting those stars. And you can look at it different ways. You can either look at an absorption spectrum, so that's when the light is passing through a filter, and so some of the different frequencies are going to be absorbed, or at the emission spectrum, which is what we did today in the demo. So this one is like the negative of that, if you want. Right? So if you start with a white illumination, then you pass through this specific element. It's going to absorb specific energy. Or if you excite the element, then it's going to emit those specific lights.
So does that mean, like, so if you look at the emission spectrum, you can tell what elements are in?
Yes, absolutely. And that's what I suppose we are going to hear in a minute. Yes, so because then, yes, indeed, there are specific lines associated to each element. So by analyzing such spectrum, we can reconstruct it or find out which are the specific elements. So you have a presentation ready? And then we need to select. Okay. All right, very good. Thank you. Go ahead.
Okay, so we're going to present on the use of atomic spectroscopy in astronomy. I'm Emma.
I'm Ryan.
That's right. Okay, so a little bit with the history. It started off with the boy Joseph here, and he put a prism at the end of a telescope, and he saw the absorption lines and he noticed them. And that's basically all he did. He just kind of saw them and was like, oh look, these exist. He didn't really do much with it. He died before he could really go into depth on it. But he was the first person to really actually put the prism there and to see them and document them. And then in 1859, Gustav Kirchhoff and then Robert Bunsen characterized the dark lines. So they noticed that for each specific element that they gave off different lines, like we saw with our diffraction ratings. So that's what they noticed, and they were like, okay, so each element has a fingerprint, if you will, which is like the presence of the different lines on the spectrum. And then they mostly just used it at the beginning when it was kind of first discovered. They just mostly used it as far as astronomy goes. They looked at the sun. They're like, oh, hey, this object is most relevant to us. It's bright, so we're going to find the spectrum of this star. So that's what they did. They started with the sun, and then they moved to other stars eventually, once they could see them well enough to actually get a spectrum for them and had better telescopes. And then once they moved to the other stars, they started using it for the star classification. So, and then there are the 7 main types. There's an O, B, A, F, G, K, and N. And then there are subcategories within those. But they kind of, the intensity of the elements present in the spectrum, as well as the intensity of the lines within it, help determine the classification of stars. So O stars are going to have the most intense and the most lines. They're the hottest. They produce the most elements. And then N, B is the most. No.
So what is spectroscopy? Basically, it's about how matter interacts with light, and especially with things like a discrete spectrum. So different elements emit and absorb different wavelengths, as we saw here. And here's an emission spectrum on the bottom, like what we just saw, and then an absorption spectrum. So when the electrons go down in energy, they emit the photon at that certain frequency, and when they go up in energy, they absorb the photon.
And that's for hydrogen.
Yes. So the Bohr model of the atom is what we've been talking about. There's the distinct energy levels. Only certain energies are allowed. And so when the electrons transition, they absorb or emit a photon with an energy equal to the difference in energy between the levels. And by looking at this, and we know what energy levels different atoms have, different elements, by looking at the spectrum, we can tell what elements are present in what we're looking at. And this is the spectrum from the sun. You can see there's a lot of bright lines and then a lot of dark lines where those wavelengths are getting absorbed.
And if we were to look at them with our very basic ratings, it will look like a continuum, but indeed because there's all those lines and we need a more accurate instrument to see those specific lines. Kinamo?
Is that the absorption or the emitting spectrum?
So this is the absorption. So there's like the sun's atmosphere. So a lot of objects will emit more continuous spectra, but then something like a gas can absorb the photons, especially if it's cooler. So the sun's atmosphere absorbs a lot of these things.
So the dark lines are the lines corresponding to the sun.
So looking at these, we can see the red and the blue shift, the Doppler effect, if you will. So a red shift means that the star is moving away from you, and then also it correlates to the speed as well. So the more intense the red is, the faster it's moving away from you, and then the less intense, the slower. And then one thing about this is that this is just for the spectrum, right? I was doing a 127 review the other day, and I said, if you have a red star and it's moving towards you, is it going to look blue? And they were all like, yeah. And they were so confident, but that's not the case. It's just the spectrum is shifted towards the blue side, rather than the star actually looking like a different color, right? And then the same goes for blues. Yeah, we can use this. We use this in galaxies, and we're looking. One of my professors said one time, and he was just a credible source, Dr. Ragazine, so I'm going to go with it. But he said, he was saying how in the sun we can use the Doppler shift on the sun to see like the movement of the sun. The sun goes in this tiny little orbit by itself because the planet's still with the sun. So he was saying how we can use the Doppler effect to calculate if the sun's moving towards us or away. We can use it to calculate the distance being as small as half a meter of the sun moving away towards us, which I thought was very interesting. And we can use this for other stars and galaxies too to get periods.
And you might have some problems trying to apply this in other areas.
Okay. All right. So is that your last slide?
One more. Sorry, it's moving fast. So this one's just about how like the instruments work. So at first they would just put a prism at the end of the telescope, and the way that works is the light goes in, and then different wavelengths of light have a different refraction angle, so it'll show up at a different spot. But now mostly they put diffraction lenses on the use series of mirrors and then the diffraction lens. And the way that works is that you have the lens, like if you think of water going through lines, like the ripples will go in one spot and then another. It kind of works like that, but with the light, and then the wavelengths will cancel out at different peaks and valleys, and then certain wavelengths will show up on a certain side of the spectrum.
But the idea is the same thing, that those gratings we were using today, but it's just more refined and very precise instruments based on this same idea, diffraction. That's it. Well, thank you very much, Emma and Ryan. For this insight on how we can apply this to astronomy. So I just want to use the last few minutes to at least go over this notion of discrete spectrum and how it was established by Rydberg and Wagner, and this formula, which is now known as the Wagner-Rydberg formula. And that's, by the way, the original documents that they wrote, the paper. Can you recognize the formula here? So they had some some integers here. At the time, it was not a quantum number, it was just an integer that they had to introduce. They found they had to introduce that in order to explain the specific positions of those lines, trying to find a relationship between them. And then they found that there was indeed a relationship. And the relationship was given by a formula like that, where you had to take the difference between two ratios, one over a certain integer squared minus 1 over another integer squared. So another way to write this more clearly is just doing that. So when you take this difference, it turns out that it's proportional to 1 over the wavelengths, you know, the specific values for the wavelengths, lambda 1, 2, 3, 4. They would follow such a formula. And the coefficient you have here is known then as the Rydberg constant, which is provided also in the book. Okay? Then just how to explain this formula? As we said, it's because of the quantization of the energy level. So I just want to go maybe through this last slide. The idea here, how to explain that. And it was first introduced by Niels Bohr. And please don't disregard this explanation because it's a very important explanation and actually, you know, correct to some extent. So it's a fundamental explanation to introduce quantum mechanics. It's what we call a semi-classical description. What do you mean by semi-classical? Yes, Abby?
So maybe sometimes it applies in quantum, but usually it applies in classical.
So it's not that sometimes, but it's just part of the explanation is classical, but then the rest of it is quantum. Is that what you wanted to say, right?
Say something like, the math works in quantum, but the way we look at it, the model looks like it's classical.
Absolutely, what you say is kind of true. So the model itself, we start with a classical model of an electron orbiting a nucleus, and we assume that we know where the electron is, we know the position, the velocity, the acceleration. So we'll just apply the classical law, which is Newton's second law. And this, when you apply that, you have mass time acceleration. This is mass time acceleration. Can you recognize an acceleration here? It's a centripetal acceleration when you have a circular uniform motion, being equal to the force. And what is the main force here? The electromagnetic interaction, the Coulomb interaction between the nucleus, which is positively charged, and the electron, which is negatively charged. And this is the force. And that was what we'll be using here in the model, just finishing with that. But the new idea Bohr introduced was the notion of quantization of the angular momentum. That the angular momentum, even using this classical model, you can apply this notion of quantization of angular momentum. This is the expression for angular momentum, and we say it's quantized. So that's why we introduce this quantum number n, integer, which is quantum number, and the unit is h bar for angular momentum. That's a new idea, and it led indeed to the quantization of the energy level. So it's a very good, actually, model to a first approximation. I'll let you go and we'll finish that on Friday. Good luck with your homework. And we'll